Welcome to part 3 of the Acids and Bases lecture. In this section, we will look at calculations related to weak acids and bases. In the earlier section, we saw how to calculate the pH of strong acids. The calculation was pretty straightforward because strong acids are completely ionized to give H3O plus ions. For example, 1 molar of HCl would give you 1 molar of H3O plus ions. But we cannot use the same method for weak acids because weak acids are not fully dissociated. A solution of a weak acid is actually a system in equilibrium where there are both undissociated and dissociated acid molecules present. Since this is a system in equilibrium, if we know the equilibrium constant, we can calculate the concentration of H3O plus present, and then we can calculate the pH of the solution. So let's look at the acid dissociation equation of a weak acid. Let's use formic acid HCOOH as an example. The equilibrium constant is called the acid dissociation constant and is written as Ka. A stands for acid. Ka equals to the concentration of the products, which are H3O plus and HCOO minus, divided by the concentration of the reactant, which is HCOOH. How about the concentration of H2O? Remember that H2O is a pure liquid and its concentration will not change, so it is not included in the equation. Ka values can be very small, so sometimes we use pKa instead to represent the strength of a weak acid. pKa equals to negative log Ka. This equation here. Both of these equations are important equations to remember. So for any weak acid in general, a weak acid could be represented by Ha. The acid dissociation reaction is represented by this equation. Ha plus H2O forms H3O plus A minus. For weak acids, remember to use a reversible arrow. The acid dissociation constant Ka equals to the concentration of H3O plus times the concentration of A minus divided by the concentration of Ha. Finally, pKa equals to negative log Ka. Among the weak acids, there are relatively stronger and relatively weaker weak acids. By comparing the Ka or pKa values, we can tell which acid is stronger or weaker. Stronger weak acids would dissociate to a greater extent, resulting in a relatively higher concentration of H3O plus and A minus, if you look at this equation. So looking at the equation for Ka, a higher concentration of H3O plus and A minus would result in a higher Ka value. We can see from this example of nitrous acid and carbonic acid that nitrous acid, which is a stronger acid, has a higher Ka value compared to carbonic acid. On the other hand, pKa values decrease when Ka increases, so stronger acids would have lower pKa value compared to weaker acids. Now, test your understanding by answering the questions in this slide. Press pause to try it out yourself, then press play to view the answers. pKa is calculated using negative log Ka, so you should get 4.77 and 3.17. Comparing the two acids, hydrofluoric acid is the stronger acid since it has a higher Ka value. The conjugate base of an acid is the acid minus a H plus ion. So for acetic acid, the conjugate base is CH3COO minus, and for hydrofluoric acid, the conjugate base is F minus. Now let's try calculating the Ka of a weak acid, chlorobenzoic acid, given that a 0.1 molar solution of chlorobenzoic acid has a pH of 2.5. To solve this question, let's first write the acid dissociation equation. This is a system in equilibrium, so let's construct an ICE table. H2O concentration will not change, so we only need to consider Ha, H3O+, and A-. Let's imagine that the acid is just dissolved in water and has not yet dissociated. This would be the initial concentration. After some time, the acid dissociates and an equilibrium is reached between Ha, H3O+, and A-. This would be the equilibrium concentration. Now, if you feel confident, you can press pause and try to fill up the table. Then press play to check your answer. At the start, we have 0.1 molar of chlorobenzoic acid. Since the chlorobenzoic acid has not yet dissociated, then H3O+ and A- concentration would be 0. We are also told that the pH of the solution is 2.5. So from this pH value, we can calculate the equilibrium concentration of H3O+ by taking 10 to the power of negative pH. Now we can fill this value into the table. With this, we can also fill in the change in concentration. The stoichiometric ratio of Ha to H3O plus to A- is 1:1:1. But since Ha is a reactant, it will be consumed, whereas H3O plus and A- will be produced. Finally, we can calculate the equilibrium concentrations of Ha and A-. Now that we have a complete set of equilibrium concentrations, we can calculate the Ka of chlorobenzoic acid. Sub the values into the equation to calculate Ka, and you should get 1.03 times 10 to the power of negative 4. Now let's try another question where you are given the Ka of a weak acid, HNO2, and are asked to calculate the pH of a 1.5 molar HNO2 solution. Once again, let's start by writing the acid dissociation reaction. Let's also construct the ICE table. Now let's try to fill up the table. We can fill in the initial concentrations. Let's imagine that the acid is just dissolved in water and has not yet dissociated. The initial concentration of HNO2 would be 1.5 molar as given in the question, while the concentration of H3O plus and NO2 minus would be 0. This time, we don't have any more data to fill into the ICE table. So let's represent the change in concentration with X. From the acid dissociation reaction, we can see that the stoichiometric ratio of HNO2 to H3O plus to NO2 minus is 1:1:1. So the magnitude of change in concentration would be the same for all three chemicals. But since HNO2 is a reactant, the concentration would decrease. That's why we write minus X. H3O plus and NO2 minus are products, so their concentration would increase. That's why we write plus X. Finally, let's fill in the equilibrium concentrations. Now let's write the equation for calculation of Ka. Then let's sub the values that we have into the equation. Now we end up with a quadratic equation, which has x squared and x. If you like, you can solve for x using the quadratic formula. This would give you an accurate value for x. But if the Ka value is small, we can make an assumption to simplify the equation and get an approximate value of x. X would usually be a very small number, so we can say, assume that x is much smaller than 1.50, then 1.50 minus x would still be approximately 1.50 over here. With this simplified equation, we can easily solve for x. If you have solved this equation using the quadratic formula method, you might have a slightly different value for x, but the value should be quite close. Now that we know the value of x, we know the H3O plus concentration, because H3O plus concentration is X at equilibrium. Then we can now calculate the pH using negative log H3O plus, and the pH is 1.56. We've looked at Ka and pKa for weak acids. Weak bases also have a corresponding Kb and pKb. B stands for base. Let's use ammonia NH3 as an example. Ammonia dissociates in water to form NH4 plus and OH minus. The base dissociation constant Kb is the concentration of the products, which is NH4 plus and OH minus, divided by the concentration of the reactant, which is NH3. Once again, remember that H2O is not included in the calculation of Kb. And as for pKb, pKb equals to negative log Kb. So for any weak base in general, a weak base could be represented by B. The base dissociation reaction is represented by this equation. B plus H2O forms BH plus and OH minus. For weak bases, remember to use a reversible arrow. The base dissociation constant Kb equals to BH plus times OH minus concentrations divided by concentration of B. Finally, pKb equals to negative log Kb. Similar to Ka for weak acids, Kb also tells us the strength of a weak base. A stronger base would have a higher degree of dissociation in aqueous solution, therefore it would have a larger Kb value. We can see from this example of S2- and formate ion that S2-, which is a stronger base, has a higher Kb value compared to formate ion. On the other hand, pKb values decrease when Kb increases, so stronger bases would have a lower pKb value compared to a weaker base. Here I'll show you another equation called the Henderson-Hasselbalch equation, which is very useful especially for buffer solutions. This slide and the next slide shows you how the equation is derived. The derivation is shown for your interest if you want to know, but I will not be testing you on how to derive the equation. This, at the bottom, is the Henderson-Hasselbalch equation. As I mentioned, you don't need to remember how to derive the equation, just remember the equation itself. We'll be using this equation in the next section on buffers. If you search for pKa and pKb values for weak acids and bases, sometimes you will find that only one of the values are reported. For example, what if you want to know the pKb of the ethanoate ion CH3COO-? But when you search for information, you can only find the reported pKa value of ethanoic acid CH3COOH. This slide shows how the Ka of a weak acid is related to the Kb of its conjugate base. We find that the pKa of a weak acid and pKb of its conjugate base are related by this equation. pKa plus pKb equals to 14. Again, you just need to remember this equation. I will not test you on how to derive this equation. So coming back to the question, given that the pKa value of CH3COOH is 4.77, what is the pKb value of CH3COO-? Press pause to try the question yourself, then press play to view the answer. Since we know that pKa plus pKb equals to 14, we can calculate the pKb of CH3COO- by taking 14 minus 4.77. The answer is 9.23.